Today we will be talking about molecular geometry and basically the shape of molecules formed by covalent bonds and why they form these shapes. And the example bond, or excuse me, the example compound we'll be using for this lesson will be SO2, which is sulfur dioxide. And just some background on the chemical sulfur dioxide. Sulfur dioxide is essentially an air pollutant that is toxic for humans, and it can be found in the pollution that comes out of factories, as can be seen in this picture right here. And it can also be found in volcanoes, and it's part of the toxic fumes that are emitted when a volcano erupts, as seen by this on the picture on the right is a picture of a volcano erupting, and that gas plume is SO2. And so basically to analyze SO2 structure, we have to create a Lewis diagram or a Lewis structure. So to create a Lewis structure of SO2, the first step is to calculate the number of valence electrons SO2 has, or the elements in SO2 has. So the first element in SO2 is sulfur, and sulfur is located on group 16 of the periodic table, meaning that it has 6 valence electrons. And oxygen also has 6 valence electrons because it's also located in group 16. So since there's 2 oxygens, let's take 6, which is the number of valence electrons, and multiply that by 2 since there's 2 of them. And once we do that, we'll get 6 plus 12, which will give us, which will give us 18. So for our Lewis structure, the overall number of electrons we want to have in it is 18. So to start out our structure, let's start out by drawing our lone element first, which is S. So this will be our middle element. And on either side of it, we'll have O, or oxygen, connected by a single bond to begin with. And so now that we have these two, let's draw 6 electrons around it, each one. So it has a total of 8, since each bond represents 2 electrons. So I'll do the same thing over here. Okay, so now that we've done this simple thing, we have to count up all the number of electrons in our diagram to make sure that it all adds up to 18. So here we have 2, 4, 6, 8, 10, 12, 14, 16. So as you can see, we're missing 2. So to get these 2, the first thing we have to do is add 2 extra ones onto sulfur, because sulfur also has to have a total of 8, just like the oxygen do. So let's add 2 more onto sulfur. And this gives us 18, but sulfur it's not fulfilling the octet rule, meaning it doesn't have a total of 8 electrons connected to it. So in order to do this, we have to create a double bond with one of our oxygen atoms. So if we create a double bond, we'll take 2 of the electrons that this oxygen has and transfer it to the bond with sulfur. And since each of these bonds equals 2, if we count up all our totals, we'll have 2, 4, 6, 8, 10, 12, 14, 16, 18, which is the number that we wanted. So now that we have 18, we've successfully created this Lewis structure. However, this structure isn't as accurate as it could be. We have all of the correct bonds. We don't have the correct angles or the correct shape of this molecule. So in order to do that, we have to essentially look at the number of electron regions and how many bonding electron regions there are and how many lone electron regions there are. So if we look at the number of electron regions that our molecule right here has, we will be able to find out the shape of it. So the electron regions are basically places around the places around the atom where electrons can be found. So if we look at sulfur, the first obvious electron region is this one right here. Formed by this bond right here, and all of these electrons are in that electron region. The next electron region is right here, which are the ones formed with its bond with oxygen. And the final electron region are the 2 that are off by itself, that are unbonded. And this makes up the final electron region. So now if we count out the electron regions, the total number is 3. The number of bonding electron regions, which are the ones that have bonds, would be 2, because these 2 right here, 1 and 2, are shared. So these two mean that there are there's a pair of bonding electron regions. And finally, that we have to count the number of lone electron regions. So the lone electron regions would be this one up here, where there's just these two electrons all by themselves. So these two electrons make up the last region, and they're the lone pair, so it's 1. So since this chemical has a total of 3 electron regions, has 2 bonding electron regions, and has one lone pair of electron regions, we know that this Lewis structure will have a bent shape. And so if we were to draw it, we would draw it once again with sulfur in the middle. We draw the 2 dots up top. However, when we're drawing our bond lines, we would draw them at a 118.6 degree angle, so approximately 119 degrees. So it'd be bent like this. O down here with its 2, or with its 4 around here, and another one down here with its 6 around it. So yeah, this would be how you would more accurately draw SO2. And here's a bit neater of a diagram of it, so I redrew it out, and as you can see right here, I once again drew it at a 118.6 degree angle. So now that we have this molecule Lewis dot structure sketched out, we can determine the polarity of the different bonds found in this structure and in this compound. So polar bonds are pretty much covalent bonds in which the electrons are not shared equally by the 2 atoms involved in the bond. And this occurs because of differing electronegativity values, which is basically a measure of how much an atom attracts an electron. And electronegativity can be found by looking at the periodic table. So a trick for memorizing how electronegativity works is by drawing an E with the arrow pointing up and to the right. And so basically, if you look at the periodic table, the elements that are going higher to the right would have a higher electronegativity than the ones that are lower and to the left. So if we look at the two elements that are in our compound sulfur dioxide, we have sulfur and oxygen. And sulfur and oxygen are both in group 16 of the periodic table. However, oxygen is, and since they're both in the same group, this means that they have a pretty similar electronegativity. However, since oxygen is higher than sulfur, its electronegativity would be slightly greater. So if we look at the bonds that we have here, and knowing the electronegativity, and knowing that oxygen has a slightly higher electronegativity, we could say that the electrons in these bonds where it is shared, that these electrons would want to spend a tad bit more time around oxygen. So this means that overall, there's not very much polarity in the bonds between sulfur and oxygen. However, there is a little bit, and this compound as a whole would be considered a polar compound. First off, because of the polarity of the slight polarity of the bonds, and also since it's a curved structure or a bent structure, and bent structures are always considered polar. So now that we understand a bit more about polarity and electronegativity, let's talk a bit about electron configuration and orbitals. So basically, electrons are found in orbitals according to a wave mechanical model. And these are basically just basically just places electrons are found. So there's 4 distinct types of orbitals. The first being s orbitals, the next being p orbitals, then d orbitals, then f orbitals. And each of these orbitals can hold 2 electrons. Each of these can hold 2. And I don't want to draw them for all of them, but you get the idea. So basically, since there's only one type of s orbital, as you can see in this diagram, s orbitals can only hold 2 electrons. And since there's 3 types of p orbitals can hold 6 electrons. And for d orbitals, since there's 5, they can hold 10 electrons, each of them holding 2. And for f orbitals, since there is 1, 2, 3, 4, 5, 6, 7, 8, they can each hold they can each hold 16, or yes, they can each hold 16. Wait, no, this is not 8. There's 7. I'm sorry. They can each hold 14 electrons. So using this information, we can essentially write out what the electron configurations will be for each of our different elements found in our compound sulfur dioxide. And if you look at this table, if we wanted to find out how many energy levels each one has, we could use this chart right here. So as you can see, in the first energy level, you can only hold one s orbital. So that means that the first energy level will only have 2 electrons. The next energy level 2, can hold an additional s orbital, and it can also hold a p orbital. So if we add another s orbital, that's adding another 2 electrons, bringing our total up to 4. And if we add a p orbital, that's adding another 6 electrons, bringing our total up to 10. And so, as you can see, as you can continue going up in orbitals, or up in energy levels, you add on another orbital each time. So the first energy level can only have s, number 2 can have s and p, number 3 can have spd, and 4 can have spdf. And after that, it just keeps going up with all of the energy levels having all of the different types of orbitals. So, if we wanted to look at how many energy levels and how the electron configurations are in our first element in our compound, which would be sulfur, we would do it like this. So since we know that sulfur has 16 electrons, 6 valence electrons, we can use we can calculate how many energy levels we need and how many electrons will be in each one. So as you can see, I've already done it here. In the first energy level, we would have one s orbital, meaning that we'd have 2. So we'd have to go on to another energy level. For the next energy level, we'd have another s orbital, which will give us another additional 2, giving us 4 in all. And we'd also have another p orbital, which would give us 6 and 6, which would give us 10 in all. And since we need a few more still, we'd have to go on to another energy level. So for energy level 3, we'd once again add on another s orbital, which would give us an additional 2, making our total number of electrons 12. And we also have to add an extra p orbital. But this one is slightly different because usually p orbitals would have 6 electrons, but since our total is only 16, and if we added 6 in our p orbital, we would have 18. This particular p orbital will only contain 4 electrons, so our atomic number for sulfur will be 16. So now let's look at the electron configuration for the second element found in our compound, which would be oxygen. And so now for oxygen, the atomic number for oxygen is 8. So with this in mind, as you can see, I've already calculated the number of energy levels we'll need. So in the first energy level, we'll have one s orbital, which will give us a total of 2 electrons. And since 2 obviously isn't enough, we'll have to go on to a second energy level. In our second energy level, we'll add another s orbital, which will give us an additional 2 electrons, giving us a total of 4 electrons. And we'll also add on a p orbital, which usually would have a total of 6. However, if we added on 6 to our already total number of 4, we'd have 10, which would be over the number we need. So to compensate for this, we'll only have 4 electrons in our p orbital to give us a total of 8. So this is basically the electron configuration for oxygen. And one more thing I'd like to mention is that you can tell the number of valence electrons an element has simply by looking at the number of electrons in its outer ring. So if we look at our electron configurations both for sulfur and for oxygen, let's look at our last outer ring, or our outer ring, our last ring, which for sulfur would be our third energy level. In our third energy level, we have an s orbital, which gives us 2 electrons, and we also have a p orbital, which has 4 electrons in it. And by looking at this energy level, we see that 2 plus 4 is equal to 6. And since sulfur is in group 16 on the periodic table, it also has 6 valence electrons. And so we can see this just by looking at our electron configuration for our different orbitals. And the same goes for oxygen, which is also in group 16. So if we look at our outermost energy level in this case, which is energy level 2, we'll see that it also has one s orbital containing 2 electrons and a p orbital containing 4 electrons, giving us once again an outer ring of 6 valence electrons, proving that we successfully did a correct electron configuration. So This essentially concludes my lesson on electronegativity, on polarity, and on molecular structure. So thank you very much for listening.